Hi, welcome to Calculus 2. Today's lecture is Calculus in Polar Coordinates. We are going to talk about area, arc length, and slope, and do several examples to make sure you understand these concepts in polar coordinates. Of course, doing the entire calculus in polar coordinates is going to take a lot more time. You remember we went through this issue once before, uh, and that is when we started with calculus in parametric curves. So there's a very long list of topics. It easily can take half a semester to go through all of these. So we are going to be choosing a few topics to go through, and hopefully you go and discover the rest of them for yourself. First concept is the concept of area. How can we calculate area between several curves in polar coordinates? As you notice, the main concept in calculus is to find simple elements of what we want to measure, and based on that create an integral that is going to give us the required quantity. So what is the simplest area in polar? Simplest area, of course, is for a circle. If you have a circle of radius r, the area of it is well, pi r squared, you know, from elementary school. What if we take a sector of this? So if I have a circle and just pick a sector. Well, how do we describe a sector? A sector has a radius r, a central angle theta. What do we know about the length of the arc in front of this? You know from trigonometry that just r times theta. What do we know about the area? Well, the area can be treated just like area of a triangle. That is the base times the height. Who acts as a base? Our base is just this side of the circle, and the height, well, any radius that you draw, all of them are the same length. And what was the area formula there for a triangle? Is 1/2 base times height. So the base is r theta, height is r, and then when you multiply them, get 1/2 r squared theta. Well, how do you justify this formula? It's quite easy. You can use concepts from calculus. You can cut this thing to small strips, and area of each of them can be justified because it looks like a triangle, and when you add them up you get 1/2 r squared theta. So how do we get this formula out of it? You notice that they are very similar. If r given as a function of theta, and let's assume r is positive, and you're going from a small angle alpha to say big angle beta, and you are on this continuous curve and you want to calculate the area of this shaded region, what do? Well, you cut it in small strips or small sectors. Each of them is like one of these sectors. Each of them is going to have 1/2 radius squared. No, the radius is not constant. Each angle has a different radius. So 1/2 r squared, and the angle for each of these sectors is going to be d theta. So for each sector we have 1/2 r squared d theta, and then to add them we start from the starting angle to the ending angle. Again, smaller angle and a bigger one, and that gives us the area formula. So let's go ahead and practice this in some standard examples. One of the curves we looked at previously was the curve r is equal to, say, cosine of 2 theta. The main challenge there was to get a grip on what does this curve look like, so that when they give us a description of the area we want to calculate, we know exactly what we are dealing with. So in this case, you notice that we made a table and carefully drew the pieces of this curve. You notice that when we went from 0 to pi over 2, it went over a region looking like this. So that was from 0 to pi over 2, and then we continued from pi over 2 to pi. There was another piece of this puzzle, and then we had from pi to 3 pi over 2, we had another piece, and then we had the final from 3 pi over 2 to 2 pi. We went through this piece of the diagram. So important thing is to have a concept how the graph looks like and how does it evolve as theta changes. So in this particular problem, it is asking us to find for example the area of one of these petals. So that's where the complication starts. What is meant by a petal, and where does it start and when does it end? So that's what we need to have. So this rose, so this is called a rose, and is a four-leaved rose. And suppose we want to find an area of one of the petals of it. In our graphing, we should notice that by the time we go from the starting point, this is 0. From 0, by the time we come to pi over 4, at pi over 4, 2 times pi over 4 is pi over 2. Cosine pi over 2 is 0. We have arrived at the origin. So I can go ahead, for example, calculate the area of this half petal and then double it, and then I'll have my area. So I can say my area is twice because one petal is going to be 2 half petals. And what I want to calculate is 1/2 of r squared d theta. And I can go from 0 to pi over 4, 0 to pi over 4. And then what is my r? Well, my r is this one. So 2 times 1/2 is just going to be 1, and 0 to pi over 4. And then I have cosine of 2 theta, which is my r, and squared d theta, and that is going to do the job for me. Now, after this, all that is left is trigonometric integrals, and we might as well get help with some identities we had. You remember the cosine of 2 theta, 2t, let's say, is 2 cosine square of t minus 1. So cosine square of t is 1 plus cosine of 2t divided by 2. So I can write here from 0 to pi over 4 cosine square of 2 theta will be 1 plus cosine of what now? Whatever this angle is, this is double of that. So this has to be 4 theta over 2. So I'll have 1 plus cosine of 4 theta divided by 2. Antiderivative of this thing is, of course, let's take a half out, and then I'll have antiderivative of 1. Antiderivative of cosine, that's going to be, of course, sine of 4 theta over 4. This whole thing between 0 and pi over 4. Now at 0, sine is 0. 4 times pi over 4 is pi, and sine of pi is again 0. So all that I have left is 1/2 of pi over 4 minus 0. So that's going to be pi over 8. So we are done with this problem. That was straightforward enough. Next topic up, how about arc length? Where do we get this formula from? Perhaps the biggest learning thing here is to see how you come up with the formulas themselves. Otherwise, the integration of it is just what we had at the beginning of semester, and the next challenge is, of course, what is the shape that we are dealing with and the particulars of that. Other than that, integration by itself is not the main concept here. So where does the concept of arc length come from? So remember, we had arc length a long time ago. We said we build it based on the delta x and then the delta y, and then we had the delta s, and we applied the Pythagorean theorem in that context. Now we have some kind of a curve that described to us as a function of theta, and we want to go from some starting angle to some ending angle. So this is our setup. Again, alpha in the bigger angle beta, and we want to find out we want to find out how long this curve is. That's our objective. Now let me go ahead and exaggerate the slope a little bit so that we have a better view of what is happening. So suppose I have a curve, let's say like this, so that we go and concentrate on a little bit of this curve. So I'm going to look at this piece of it. How would I approximate that? Here's how I go about looking at this. So suppose I draw a little circle here, and suppose this angle here is d theta, a small angle d theta, and suppose this radius is r. Well, how long would this side be? You remember that we said the arc subtending the central angle is just the radius times the size of that angle. Therefore, in this context, this will be r d theta. Okay, this angle was d theta, radius is r, and I make a circle here, and that's r d theta. How about this length? Well, r is changing, and as we go up or down, there's going to be differential of r indicating how the r is changing. Now, the arc length in front of this angle, let's call it dl. We can apply Pythagorean theorem here. The length of this hypotenuse squared is the length of this one squared, which is r d theta squared, and then the other length squared, which is dr squared. So I can write dl, the element of length is square root of r d theta squared plus dr squared. Well, next I can go ahead and factor my d theta squared, and then I'll have r squared plus, there is no factor of d theta here, but I can put it in a denominator, just like a fraction. Then I can take d theta outside, so we'll have d theta square root of r squared plus, now who is dr d theta? That's the derivative of r with respect to theta. That is what we agreed as a matter of shorthand, dr d theta or df d theta, and let's abbreviate it to r prime, so that is just r prime squared. So if I want to find the length, what do I do? The arc length, I'll take this expression r squared and derivative of r squared times the element of angle, and then integrate it from starting angle to the ending angle. So whatever the starting angle is to whatever the ending angle happens to be, I integrate along that. Okay, again, the issue now boils down to just doing the integral. But again, the main challenge is to have an idea of where something starts, where it ends, and what's an actual curve that you are integrating on, and some various complications that could occur in any kind of situation. So let's go ahead and practice in a simple setting. For a more elaborate proof, you can read your text. Let's go take an example. The question is find the length of now first we go get an idea of what this curve is. We have seen it before. This is a cardioid. So when theta is 0, r is 1, we start let's say at this point. By time theta becomes pi over 2, we have gone to 2. And then by time we hit pi, we are back to 1. So this is at 0 and pi over 2, pi. By time we are at 3 pi over 2, sine is minus 1, r becomes 0, we hit at the origin, so it is 3 pi over 2. And then as we continue, r always stays positive. By time we meet starting point, theta has arrived at 2 pi. So we said previously it looks like a heart. Perhaps I look better, a little bit better than what I drew it. But so suppose I want to find the length. So L is the integral. It's we want to go all around. So we really want 0 to 2 pi. And then the integral r squared. R itself is 1 plus sine theta. How about r prime? R prime is, well, derivative of 1 is 0, derivative of sine is cosine. R prime is this. And then I have to integrate. Let's clean up a bit. This integral becomes 1 squared plus 2 sine theta plus sine square of theta plus cosine square of theta d theta. As usual, this is just 1, so this becomes integral from 0 to 2 pi of 2 plus 2 sine theta d theta. Okay, now we are facing an integral. So the integration of r squared plus r prime squared in square root provides us the length. Next step is integration. All sort of trick substitution might be used here, and a variety of other things we might employ to help us do this. I'm going to follow with the following. This I can write 2 times sine theta. I can factor my 2. 1 plus sine theta. Now the problem is that this is in square root. How do we handle that? You can adopt many different ways of handling this problem. One of them is the following. We remember that identity for cosine is there. 1 plus cosine of t is 2 cosine square of t over 2. Why do I go after this? Why do I pick on this particular identity? Because my obstacle is this square root. If I had cosine instead of sine, I could use this identity and it would come out of the radical. I'll be home free essentially. So how can I change my sine to a cosine? How can I legitimately do this? Well, we have a substitution. If you use a substitution, for example, theta is equal to pi half minus u, then your sine of theta becomes sine of pi half minus u, and you know from a trig identity, from complementary angles, this is cosine of u. So this is promising because if I change my sine to cosine, then well, I can use this identity and then come out of the radical. That's the main reason I'm doing this thing. Once we do a substitution, we also need to do substitution for the differential. So this is minus du, so direction of integration is reversed. And then we have to also watch out for our limits of integral. But let's go ahead. Let me postpone that for a while. I have the integral of 2 plus 2 sine of theta d theta. This becomes integral of 2 plus 2 cosine of u. Sine theta becomes cosine of u. Instead of d theta, we'll have minus du. 2 plus 2 cosine u, 2 plus 2 cosine u becomes, well, double of that becomes 4 cosine square of u over 2. So this becomes in radical 4 cosine square of u over 2, and then put the minus here. Now, next complication. When I want to take square root, I have to watch out that square root of x squared is really absolute value of x to protect against negative. So this is going to be minus absolute value of 2 cosine of u over 2 du. Now, absolute value is not a fun object to work with or to integrate and so on. So we go after the next issue. I want to force this thing to have the same sign all the time so that I don't have to worry about the absolute value. How do I do that? I say, okay, how is my u going to behave? My u is going to be, of course, pi half minus theta. Is that right? My u is pi half minus theta. So pi half minus theta, my u, let me write it in red maybe, my u is going to be, so it starts at pi half here, by the time I arrive here is 0, pi half minus this quantity here, so continuing, u being theta, pi over 2 minus theta, at this point is going to become minus pi over 2. At this point, 3 pi over 2 is to be subtracted from pi over 2, so it becomes minus pi. At this point, pi over 2 minus 2 pi becomes minus 3 pi over 2. So let's do the following. Instead of going for the entire length, let's cut this thing into pieces so we get additional information. So I'm going to go for the following. I'm going to get this long piece here, and then this by symmetry is the same as that. Then I come and calculate this small piece. This is going to be same as that, and all of them together is going to be the length of the cardioid. Why do I do this this particular way? First of all, we get individual pieces. And the second, more troubling issue is dealing with this absolute value because the sign of this expression is going to change, and then we have to watch out for that. So uh, let's go for this big piece from 0 to pi over 2. So integral from 0 to pi over 2 of radical 2 plus 2 sine theta d theta is equal to minus 2 cosine of u over 2 du, and then we said we are using u is equal to pi over 2 minus theta. So at this point it's going to become pi over 2, and at this point it's going to become 0. So this is going to be the length of the long piece. So that's now we can exchange this negative by exchanging the limits of the integral. So it becomes integral from 0 to pi over 2 of absolute value of 2 cosine of u over 2 du. You notice that between these two angles, this is always cosine of half of this is always positive, obviously. So I can do away with the absolute value, becomes 2 cosine of u over 2 du. Antiderivative of this thing is 4 sine of u over 2 from 0 to pi over 2. It becomes 4 sine of pi over 4, and at 0 this is just going to be 0. So that's going to be 4 times radical 2 over 2, and that boils down to 2 radical 2. So what we found out is that this piece is 2 radical 2. Of course, this other piece is also going to be 2 radical 2. Now let's go for this small little wiggle at the bottom. So what are the limits of that integration? We said we are going from minus pi over 2 to minus pi. For theta, let's write the theta values first. So theta values goes from pi to 3 pi over 2 of the same integral. Pi half minus these values is going to be minus pi half to minus pi, and this is again minus 2 cosine of u over 2 du. Again, I exchange this minus with flipping the limits of the integral, so it becomes from minus pi to minus pi over 2 of 2 cosine of u over 2. Now cosine of minus pi over 2, that's of course 0. Cosine of minus pi over 4, that's also positive. So I'm in the positive territory. I can do away with my absolute value again. That's the advantage of this. Same as before, becomes 4 sine of u over 2 between minus pi over 2. So I get 4 sine of minus pi over 4 minus sine of minus pi over 2. This becomes 4 times this minus radical 2 over 2. Minus and minus gives me a plus 1. I multiply it, I get 4 minus 2 radical 2. So what we learned here is that, let me color this thing differently. This piece is going to be 4 minus 2 radical 2. This is going to be, of course, same. So what we have is the length becomes upper piece we had 2 radical 2, then there is another one by symmetry 2 radical 2, and then the bottom piece was 4 minus 2 radical 2, another bottom piece 4 minus 2 radical 2, by symmetry they're the same. Of course these radicals cancel each other out, and out comes 8. Surprisingly simple answer. The length of the cardioid became 8. Notice that we also calculated each significant piece of the cardioid, so we have the additional information. What else did we promise that we are going to do? Finding the slope. Okay, so one of the basics of so the overall plan was calculus in polar coordinates. We chose 3 topics to follow: area, arc length, and slope. Let's go after slope. Where does this formula itself come from? So we want to find the slope, which in calculus 1 is simply dy dx. Well, this is an example of what we did for parametric equation. We just apply that case here. We know that our transformation formulas are r cosine theta for x and r sine theta for y, and r itself now is taken to be some function of theta. Now if I want to calculate dy dx, just like what we did for parametric equation, I can calculate dy d theta divided by dx d theta. That was from the chain rule. So d theta of r sine theta in the numerator and d theta of r cosine theta in the denominator. Well, now we have to apply the product rule. Derivative of the first we are abbreviating as r prime. R prime is the derivative of r function or f function, either way. So r prime sine theta plus r times derivative of sine, which of course is going to be cosine. In the denominator we'll have r prime cosine theta, and now minus r, derivative of cosine is sine theta. So let's go and do an example of this. A good example again is that cardioid we looked at. Let's continue with that cardioid. So let's consider find say slope of tangent line, slope at pick any angle you want, like pi over 4. Also find the top and bottom, right and left, so top, bottom, right and left of cardioid. What do we mean by that? Well, it's typical that if you have a curve, you want to know what's the top point, what's the bottom point, what's the rightmost point, what's the leftmost point, and so on, as if you are making a bounding box, if such a thing is possible. Top and bottom are of course where dy dx is 0. And right and left is where, if you wish to think, either dx dy is 0, or if you would like to think about it, is that dy dx is undefined or is infinity, assuming the other derivative is not 0. So first, what is dy? What is the slope? Slope, we said dy dx. We have a ready-made formula for it. R is 1 plus sine theta. So r prime, let's write r prime is going to be cosine theta. So I'll have cosine theta sine theta plus 1 plus sine theta times cosine theta divided by r prime, which is again cosine theta times another cosine theta minus 1 plus sine theta times another sine theta. You might try to simplify, that much. Sine cosine, another sine cosine. So I'll have cosine theta plus 2 sine theta cosine theta. Denominator is cosine square theta. Minus sine square theta, and then minus sine theta if you wish. If you want to simplify, not sure how much we earn by doing this thing, you can apply some trig identity. This is cosine theta plus sine 2 theta, double angle identity. This is cosine of 2 theta minus sine theta. That's another expression you could get. And then you can evaluate this thing at whatever point they gave you. So theta is equal to pi over 4. Slope becomes, let's use this one. So cosine, everything becomes radical 2 over 2 plus 2 radical 2 over 2 times another of the same, and then radical 2 over 2 squared minus another radical 2 over 2 squared minus radical 2 over 2. So what does it become? So it becomes radical 2 over 2. This becomes a 2 times a 2 is a 4. Divided by 4 is just a 1. This is of course 0 minus radical 2 over 2. Can multiply numerator denominator by a 2. So that's our slope. So what does this mean? We had that cardioid, let's say something like this. We are going at 40 pi over 4. At this point we are asking what is the slope of this. Maybe I go ahead and multiply this thing by radical 2, maybe makes it a little bit nicer. It becomes a 2 plus 2 radical 2 over minus 2, and then that becomes minus 1 plus radical 2. So that's clean enough. Slope is minus 1 plus radical 2 at this point, for whatever that is worth. Now, well, what are the high and low and left and right? So of course this high point is right here, so we better recover theta equal to pi over 2 or x equal to 0. Bottom, more interesting though. Bottom, there are two bottom points, these two. We want to catch those, and then we want to catch at what point this tangent become vertical. Two of those as well. So suppose I want to find the top and bottom points, and that means dy dx is 0. So at the top and the bottom, this is what's going to happen. Well, the numerator is this one, so cosine theta, sine theta plus 1 plus sine theta times cosine theta. I want that to be 0. I might as well factor cosine. Here I get 1 plus 2 sine theta. I want this to be 0. Did I do this right? So sorry, this tells us either cosine theta is 0 or 1 plus 2 sine theta is 0. This tells us angle is either pi over 2 or 3 pi over 2. So pi over 2 obviously is this. 3 pi over 2 hour is a problematic point. What happens at 3 pi over 2? Uh, so let's rewrite our derivative to double check to see what's happening at these 2 points. Nothing unusual at pi over 2, but this 3 pi over 2 is deserves more attention. So let's rewrite dy dx. We had this expression cosine theta times sine theta plus 1 plus sine theta times cosine theta divided by cosine theta minus 1 plus sine theta times sine theta. Okay, that's fine. At pi over 2, nothing unusual happens. This is 0, this is 0, okay, 0, 0, this is 1, this is 2, so 0 divided by minus 2, divide the x as expected is 0, nothing eventful over there, that's just horizontal tangent line. How about at 3 pi over 2? At 3 pi 2, cosine again is 0, but what happens now is that this is 0, cosine of 3 pi over 2 is 0, this is 0, and 1 plus sine is also 0 because sine of 3 pi over 2 is minus 1. So our expression is going to become 0 over 0. And what is that? Let's postpone that for a second because so the question is what happens? Graphically we see that there is a cusp there, and that cusp indicates the vertical tangent line. So how did we decide 0 over 0 in calculus 1? Of course we had L'Hopital rule. We can apply L'Hopital rule to this, but this is a little bit lengthy. Let's go ahead and apply L'Hopital rule to that. So as theta goes toward 3 pi over 2, I want to know what's the limit of this expression. So I take the limit of cosine theta plus sine of 2 theta over cosine of 2 theta minus sine of theta as theta goes toward 3/2. We notice that this is 0 over 0. L'Hopital says, well, differentiate numerator, you get minus sine of theta plus 2 cosine of 2 theta divided by minus 2 sine of 2 theta, and then this one is minus cosine of theta. Now I have to look at the limit of this as theta goes toward 3/2, 3 pi halves. So this is minus 1. This is going to be twice cosine of 3 pi, that's minus 1. Sine of 3 pi, 2 times 3 pi over 2, sine of 3 pi, that is 0. Cosine of 3 pi 2, also 0. So I'm dividing what I have here which is minus 1 by 0, that's going to be infinity. That means what we found is that the slope at 3 pi over 2 is infinity. Slope at 3 pi over 2 is infinity. It means we have a vertical tangent line at that point, and that's what agrees with our graph, that at this point we have a cusp. That cusp, the two sides approach that terminal point, so from the left it comes toward the cusp, and then on the right also like a pine needle. In the middle, what we have is a vertical tangent line. What else were we aiming for? We said we want to find out what's the rightmost and leftmost point of this cardioid. So we want to know where are these points. Let's go ahead. Well, I realized I didn't finish the previous job of figuring out the horizontal tangent lines. We have these two to care of, and that one you can see from here. Excuse me. Theta, sine of theta becomes minus 1/2, and that gives us theta equals the angle at which sine is minus 1/2, 7 pi 6 and 11 pi 6. For the second portion, we want to figure out where the tangent will be vertical. Of course, we found that at this point is vertical. Let's go after the other two. That's going to happen where the denominator is equal to 0. So let's go ahead and see vertical tangent line. We are going to have cosine theta minus 1 plus sine theta times sine theta being equal to 0. So we go ahead and multiply. I get cosine square of theta minus sine square of theta minus sine of theta equal to 0. Let's convert everything to sine so that we can solve this. 1 minus sine square of theta minus sine square of theta minus sine theta is equal to 0. So that becomes minus 2 sine square of theta minus sine theta plus 1 equal to 0. Maybe feel more comfortable by multiplying this thing with a minus, so it looks more familiar. Sine theta minus 1 equal to 0. Fortunately, these factors, if we didn't, we just apply the quadratic formula. 2 sine theta minus 1 times sine of theta plus 1 equal to 0. This tells us sine of theta is equal to minus 1, and that is where we already saw at the cusp. This is where that happens. The other one, sine of theta becomes equal to 1/2. Theta is pi 6 and 5 pi 6. And then, of course, we can put this thing in our formula to get the r. R was 1 plus sine of theta. So we can go ahead and find the r for each of these. It's 1/2, and the 1 makes 3/2. And this one also same point. So the coordinates where the horizontal and vertical tangent lines happen can be easily found. The challenge was with the cusp, and we did that with L'Hopital rule. Okay, so 3 problems we did. The ideas themselves are straightforward. You might feel a bit overwhelmed with respect to all the algebra that was needed to actually apply this in the context of a few examples like a cardioid and others. but make sure that you are comfortable with the general idea of itself. On top of that, we have integration issues from Calculus 1, uh, issues from pre-calculus and trigonometry, and those are secondary to the topic that we are covering right now. Until next time, good luck and God bless.